Interstellar travel is the term used for hypothetical manned or unmanned travel between stars. Interstellar travel will be much more difficult than interplanetary spaceflight. The distances between the planets in the solar system are less than 30 astronomical units, whereas the distances between stars are typically hundreds of thousands of and usually expressed in light years. Because of the vastness of those distances, interstellar travel would require either great speed, a high percentage of the speed of light, or huge travel time, lasting from decades to millennia or longer. The speeds required for interstellar travel in a human lifetime far exceed what current methods of spacecraft propulsion can provide, even with a hypothetically perfectly efficient propulsion system. The kinetic energy corresponding to those speeds is enormous by today's standards of energy production. Moreover, collisions by the spacecraft with cosmic dust and gas can produce very dangerous effects both to passengers and the spacecraft itself. A number of strategies have been proposed to deal with these problems, ranging from giant arcs that would carry entire societies and ecosystems, to microscopic space probes. Many different spacecraft propulsion systems have been proposed to give spacecraft the required speeds, including nuclear propulsion, beam-powered propulsion, and methods based on speculative physics. For both manned and unmanned interstellar travel, considerable technological and economic challenges need to be met. Even the most optimistic views about interstellar travel see it as only being feasible decades from now. The more common view is that it is a century or more away. However, in spite of the challenges, if interstellar travel should ever be realized, then a wide range of scientific benefits can be expected. Challenges: interstellar distances between the planets in the solar system are often measured in astronomical units, defined as the average distance between the Sun and Earth, some 150 million kilometers. Venus, the closest other planet to Earth, is 0.28 astronomical units away. Neptune, the farthest planet from the Sun, is 29.8 astronomical units away. Voyager 1, the farthest man-made object from Earth, is 130.83 astronomical units away. The closest known star, Proxima Centauri, however, is some 268,332 astronomical units away, or over 9,000 times farther away than even the farthest planet in the solar system. Because of this, distances between stars are usually expressed in light years, defined as the distance that a ray of light travels in a year. Light in a vacuum travels around 300,000 kilometers per second, so this is some 9.46 trillion kilometers or 63,241 astronomical units in a year. Proxima Centauri is 4.243 light-years away. Another way of understanding the vastness of interstellar distances is by scaling. One of the closest stars to the Sun, Alpha Centauri, can be pictured by scaling down the Earth-Sun distance to 1 meter. On this scale, the distance to Alpha Centauri would be 271 kilometers. The fastest outward-bound spacecraft yet sent, Voyager 1, has covered 1/600th of a light-year in 30 years and is currently moving at 1/18,000th the speed of light. At this rate, a journey to Proxima Centauri would take 80,000 years. Required energy: a significant factor contributing to the difficulty is the energy that must be supplied to obtain a reasonable travel time. A lower bound for the required energy is the kinetic energy, K equals 1/2 mv2, where m is the final mass. If deceleration on arrival is desired and cannot be achieved by any means other than the engines of the ship, then the lower bound for the required energy is doubled to mv2. The velocity for a manned round trip of a few decades to even the nearest star is several thousand times greater than those of present space vehicles. This means that due to the V2 term in the kinetic energy formula, millions of times as much energy is required. Accelerating 1 ton to 1/10 of the speed of light requires at least 450 petajoules or 4.5 times 1017 J or 125 terawatt-hours. Without factoring in efficiency of the propulsion mechanism. This energy has to be generated on board from stored fuel, harvested from the interstellar medium, or projected over immense distances. Interstellar medium. A knowledge of the properties of the interstellar dust and gas through which the vehicle must pass will be essential for the design of any interstellar space mission. A major issue with traveling at extremely high speeds is that interstellar dust may cause considerable damage to the craft. Due to the high relative speeds and large kinetic energies involved, various shielding methods to mitigate this problem have been proposed. Larger objects are far less common, but would be much more destructive. The risks of impacting such objects, and methods of mitigating these risks, have been discussed in the literature, but many unknowns remain owing to the inhomogeneous distribution of interstellar matter around the Sun, will depend on direction traveled. Although a high-density interstellar medium may cause difficulties for many interstellar travel concepts, interstellar ramjets, and some proposed concepts for decelerating interstellar spacecraft would actually benefit from a denser interstellar medium. Travel time. An interstellar ship would face manifold hazards found in interplanetary travel, including vacuum, radiation, weightlessness, and micrometeoroids. Even the minimum multi-year travel times to the nearest stars are beyond current manned space mission design experience. The habitual illumination energy requirement for each person is estimated to be 12 kilowatts. Other long-term energy requirements are still being investigated. More speculative approaches to interstellar travel offer the possibility of circumventing these difficulties. Special relativity offers the possibility of shortening the travel time through relativistic time dilation. If a starship could reach velocities approaching the speed of light, the journey time as experienced by the traveler would be greatly reduced. It has been speculated that general relativity might be consistent with faster-than-light travel, which could greatly shorten travel times, both for the traveler and those on Earth. Weight calculation. It has been argued that an interstellar mission that cannot be completed within 50 years should not be started at all. Instead, assuming that a civilization is still on an increasing curve of propulsion system velocity, not yet having reached the limit, the resources should be invested in designing a better propulsion system. This is because a slow spacecraft would probably be passed by another mission sent later with more advanced propulsion. On the other hand, Andrew Kennedy has shown that if one calculates the journey time to a given destination as the rate of travel speed derived from growth increases, there is a clear minimum in the total time to that destination from now. Voyages undertaken before the minimum will be overtaken by those who leave at the minimum, whereas those who leave after the minimum will never overtake those who left at the minimum. One argument against the stance of delaying a start until reaching fast propulsion system velocity is that the various other non-technical problems that are specific to long-distance travel at considerably higher speed may remain obstacles that take much longer time to resolve than the propulsion issue alone. Assuming that they can even be solved eventually at all, a case can therefore be made for starting a mission without delay, based on the concept of an achievable and dedicated but relatively slow interstellar mission using the current technological state-of-the-art and at relatively low cost, rather than banking on being able to solve all problems associated with a faster mission without having a reliable time frame for the achievable communications. The round-trip delay time is the minimum time between an observation by the probe and the moment the probe can receive instructions from Earth reacting to the observation. Given that information can travel no faster than the speed of light, this is for the Voyager 1 about 36 hours. And near Proxima Centauri it would be 8 years. faster reaction would have to be programmed to be carried out automatically. Of course, in the case of a manned flight, the crew can respond immediately to their observations. However, the round-trip delay time makes them not only extremely distant from, but, in terms of communication, also extremely isolated from Earth. Interstellar communication is still problematic, even if a probe could reach the nearest star. Its ability to communicate back to Earth would be difficult given the extreme distance. See interstellar communication. Prime targets for interstellar travel. There are 59 known stellar systems within 20 light-years of the Sun, containing 81 visible stars. The following could be considered prime targets for interstellar missions. Existing and near-term astronomical technology is capable of finding planetary systems around these objects, increasing their potential for exploration. Proposed methods: slow, uncrewed probes. Slow interstellar missions based on current and near-future propulsion technologies are associated with trip times starting from about 100 years to thousands of years. These missions consist of sending a robotic probe to a nearby star for exploration, similar to interplanetary probes such as used in the Voyager program. By taking along no crew, the cost and complexity of the mission is significantly reduced, although technology lifetime is still a significant issue next to obtaining the reasonable speed of travel. Proposed concepts include Project Daedalus, Project Icarus, Project Dragonfly, and Project Longshot. Fast, uncrewed probes. Nanoprobes. Near light speed nanospacecraft might be possible within the near future, built on existing microchip technology with a newly developed nanoscale thruster. Researchers at the University of Michigan are developing thrusters that use nanoparticles as propellant. Their technology is called nanoparticle field extraction thruster, or nanofit. These devices act like small particle accelerators, shooting conductive nanoparticles out into space. Michio Kaku, a theoretical physicist, has suggested that clouds of smart dust be sent to the stars, which may become possible with advances in nanotechnology. Kaku also notes that a large number of nanoprobes would need to be sent due to the vulnerability of very small probes to be easily deflected by magnetic fields, micrometeorites and other dangers. To ensure the chances that at least one nanoprobe will survive the journey and reach the destination. Given the light weight of these probes, it would take much less energy to accelerate them. With onboard solar cells, they could continually accelerate using solar power. One can envision a day when a fleet of millions or even billions of these particles swarm to distant stars at nearly the speed of light and relay signals back to Earth through a vast interstellar communication network. As a near-term solution, small, laser-propelled interstellar probes based on current CubeSat technology were proposed in the context of Project Dragonfly. Slow, manned missions. In crewed missions, the duration of a slow interstellar journey presents a major obstacle, and existing concepts deal with this problem in different ways. They can be distinguished by the state in which humans are transported on board of the spacecraft. Generation ships. A generation ship is a type of interstellar ark in which the crew that arrives at the destination is descended from those who started the journey. Generation ships are not currently feasible because of the difficulty of constructing a ship of the enormous required scale and the great biological and sociological problems that life aboard such a ship raises. Suspended animation. Scientists and writers have postulated various techniques for suspended animation. These include human hibernation and cryonic preservation. Although neither is currently practical, they offer the possibility of sleeper ships in which the passengers lie inert for the long duration of the voyage. Frozen embryos. A robotic interstellar mission carrying some number of frozen early-stage human embryos is another theoretical possibility. This method of space colonization requires, among other things, the development of an artificial uterus, the prior detection of a habitable terrestrial planet, and advances in the field of fully autonomous mobile robots and educational robots that would replace human parents. Island hopping through interstellar space. Interstellar space is not completely empty. It contains trillions of icy bodies ranging from small asteroids to possible rogue planets. There may be ways to take advantage of these resources for a good part of an interstellar trip, slowly hopping from body to body or setting up way stations along the way. Fast missions. If a spaceship could average 10% of light speed, this would be enough to reach Proxima Centauri in 40 years. Several propulsion concepts have been proposed that might be eventually developed to accomplish this, but none of them are ready for near-term development at acceptable cost. Time dilation. Assuming one cannot travel faster than light, one might conclude that a human can never make a round trip farther from Earth than 20 light-years if the traveler is active between the ages of 20 and 60. A traveler would never be able to reach more than the very few star systems that exist within the limit of 20 light-years from Earth. This, however, fails to take into account time dilation. Clocks aboard an interstellar ship would run slower than Earth clocks. So if a ship's engines were capable of continuously generating around 1 gram of acceleration, the ship could reach almost anywhere in the galaxy and return to Earth within 40 years ship time. Upon return, there would be a difference between the time elapsed on the astronaut's ship and the time elapsed on Earth. For example, a spaceship could travel to a star 32 light-years away, initially accelerating at a constant 1.03 grams for 1.32 years, then stopping its engines and coasting for the next 17.3 years at a constant speed, then decelerating again for 1.32 ship years, and coming to a stop at the destination. After a short visit, the astronaut could return to Earth the same way. After the full round trip, the clocks on board the ship show that 40 years have passed, but according to those on Earth, the ship comes back 76 years after launch. From the viewpoint of the astronaut, on-board clocks seem to be running normally. The star ahead seems to be approaching at a speed of 0.87 light-years per ship year. The universe would appear contracted along the direction of travel to half the size it had when the ship was at rest. The distance between that star and the Sun would seem to be 16 light-years as measured by the astronaut. At higher speeds, the time on board will run even slower, so the astronaut could travel to the center of the Milky Way and back in 40 years ship time. But the speed according to Earth clocks will always be less than 1 light-year per Earth year, so, when back home, the astronaut will find that more than 60,000 years will have passed on Earth. Constant acceleration. Regardless of how it is achieved, if a propulsion system can produce acceleration continuously from departure to arrival, then it is the fastest method of travel. A constant acceleration journey is one where the propulsion system accelerates the ship at a constant rate for the first half of the journey, and then decelerates for the second half, so that it arrives at the destination stationary relative to where it began. If this were performed with an acceleration similar to that experienced at the Earth's surface, it would have the added advantage of producing artificial gravity for the crew. Supplying the energy required, however, would be prohibitively expensive with current technology. From the perspective of a planetary observer, the ship will appear to accelerate steadily at first, but then more gradually as it approaches the speed of light. It will undergo hyperbolic motion. The ship will be close to the speed of light after about a year of accelerating and remain at that speed until it breaks for the end of the journey. From the perspective of an onboard observer, the crew will feel a gravitational field opposite the engine's acceleration, and the universe ahead will appear to fall in that field, undergoing hyperbolic motion. As part of this, distances between objects in the direction of the ship's motion will gradually contract until the ship begins to decelerate, at which time an onboard observer's experience of the gravitational field will be reversed. When the ship reaches its destination, if it were to exchange a message with its origin planet, it would find that less time had elapsed on board than had elapsed for the planetary observer, due to time dilation and length contraction. The result is an impressively fast journey for the crew.